Okay. So just so you can get a sense of these friction factors now that you're going to have to calculate for all piping problems, kind of one of like the first things you should do if you have a pipe problem is get that friction factor, because you're going to end up wanting to know how much energy it takes to get the fluid through the pipe. So what a good thing to see is that these friction factors usually lie in this range. These are how small these numbers end up being, right? You got 0.001 and you got 0.1 is where the friction factor will lie. And it's not like, and it is not the case that like all the laminar are close to here and all the turbulent are close to here, right? Because in the movie chart, you see that you have two graphs depending on where you are. But just know that the value of ranges are sort of around here. So for any sort of iterative type of thing, if you want to give an initial guess for what the friction factor is, right? I always just tell my computer to like start there and then iterate to maybe get the correct one, because I know the range that they usually lie in. Now for values of roughness heights, right? These are the rate values, just depending on the values that you have. This non-dimensional roughness height right here. This lies in a range of like to about there. So this is right, the roughness height divided by the diameter of your pipe. That ranges from like extremely small, where this is like glass, right? To like this is a fairly rough surface actually for what do we have? Anything I have there? That's good. This is a fairly rough surface. I can think of a eroded concrete type pipe, something like that. And then ones past this are sometimes considered fully rough. So those are examples of the types of quantities you should guess about where these things are. Okay. And that is helpful enough. There's also a way to more well define this fully rough concept. And that is, we use an epsilon plus notation, right? So if it's less than, we say 5, that's the fully smooth equation that I did the first turbulent friction factor equation I gave you. If this quantity is less than 5, use the fully smooth. Then you have this transitional region, which you don't ever really want to be in because you want to be in one place or the other. And then we have a better definition. It's this. So this is that fully rough curve you would actually look down for your movie chart. Or you just plug it into the formulas and it just turns out this way. And this quantity is something you maybe could calculate if you care about. It's your actual roughness height times this friction velocity divided by the viscosity rho, mu over rho. Okay, and then remember that this rho is shear at the wall divided by rho. I had to tell you this because it's in the where notes, but when it comes to calculating Moody charts, you just need to get an epsilon over rho. You don't really need to give these epsilon plus transition regions. So with that it being said, that's going to finish this lecture and give an overview of just sort of what we now know how to do, right, is given a pipe flow problem, right, with a flow rate going into it, we have properties of the fluid. Let's say we know some dimensions, so we have some dimensions of the profile. So in terms of calculating friction factors, right, we have find the Reynolds, okay, and we have two paths. We have it's less than 2,000 or greater or equal to 2,000. So this is laminar. It's turbulent. So you got to find Reynolds number. Now you get this. If it's laminar, the friction factor is just 64 divided by that Reynolds number. Super simple. If it's turbulent, right, you really got to consider what the roughness height is. I never mentioned that for laminar, we do have rough pipes, but they don't actually play a role in the laminar case. And there's research, there's arguments to show that, but it doesn't really matter to you, right? Because if it's laminar, just use this equation. I don't think anyone's really worried about why the roughness height doesn't affect laminar. I can tell you why it is later if you want. So if it's turbulent though, you should get the roughness height because it will affect these properties. And you're never really fully smooth for turbulent flows because they're usually a concrete or water piping system. So find that epsilon value. And then you can either use a Moody chart to get EF. I mean, technically you could always just use a Moody chart, but why would you use a Moody chart for laminar? Or you use Moody chart, or you just use the equation. The equation I have is that approximate one. Okay, and this approximate one was 1 over the square root of f. Approximately, I'll write it again. I don't remember this equation because I just have it in an Excel, so I don't really have to remember. I have 3.7. Right? This was the not implicit approximate fitted one, and it's good because you don't have to do any solving. It's just, there's the Reynolds number, which you calculated right there. Here's this value, which you calculated right there. Right? These are just numbers, and then you can get the friction factor. And that's really the process for these friction factors. There are some issues that come up later. I'll talk about pipe flow, like the types of problems we come into, where sometimes we're asked to find head loss, find a diameter, or find a flow rate. And there's a process folder that kind of breaks every kind of problem down into the steps that are required. Right, so the three types of problems are, you don't really know what this is yet, but we'll get there. There's find the head loss for the system, or there's find a flow rate, or there is find the diameter of the pipe. So think of this as the energy problem. This is this is the dimension problem. What dimension of my pipe should I have given constraints? And then the flow rates, the velocity, flow rates of velocity program. So I kind of sometimes I think about that as like a requirement. Kind of a requirement or constraint problem. I always think of this type of problem. I always think of this finding the Q problem for these pipe flow problems is involving, as I know, right, is that, right, I bought in a couple pipes that are these dimensions, and I only had the budget for one pump that can provide energy. So what flow rate am I gonna get from what I bought? I bought some pipes and I bought a big pump. What's my flow rate? The head loss problem, or what's the energy is the customer told me that I want this much flow rate of water in my system, and I have these pipes. This is what your project is. I'm giving you diameters and I'm giving you flow rates. And I'm just saying, give me the energy. Because I'm asking you to tell me what pump I need to buy. So what's the power requirement on the pump and how much is that going to cost me? So this is actually the easiest one. And you'll see why later. These are harder because you have to use iterative methods to solve these problems right here. So right with the Q1, you know this, you bought a pump that provides energy and you know the dimensions, so find me the flow rate I'll get. And because of the way the equations work out, you can't just write that solution out, you have to do a bunch of iterations to get there. With this one, where it's really a dimension type of problem is, I know what flow rate I want and I bought a certain pump, so like these are kind of the hard constraints that I only bought this pump and the customer is really on me that he only wants this much flow rate in the system. Could be a gas engine or something like that that's really specific to the flow rate it has. So now you need to see what diameter of pipe will give you that. But again, these ones are more difficult. The whole point of the project though is if you can set your Excel sheet or some tunable thing to just spit out the head loss every time, and you have the ability to just change these values on the fly, then you kind of have solved all of them, right? So you've taken the easy problem, and as long as you have some way to make it resolve really, really quickly, you will see that I can just change the diameter a bunch in Excel and see if I get the right head loss that I'm supposed to have, or I can change this and see if I can get the right other ones. This will become clear later on, but as of now, this is one that you can. This is one that we're getting close to calculating, but this whole lecture was just you should understand how to calculate these things. Given problem statements. So I hope that's question marks so you can remember what those equations are. So get good at this, and then next lecture we'll get good at calculating head losses based on the Bernoulli energy equation, and then after that, that's all the tools you'll need for this project. So next one will be how to calculate the head loss given these friction factors.